Hello, this is the Mathematic Fanatic, and you are watching a cool twist on the sum of Fibonacci numbers. So first off, what's the question that we're trying to find? We want to find the following sum, the sum from k equals 0 to infinity of f of k plus 1 over 2 to the k, where f of k is the kth term of the Fibonacci sequence, starting with f of 0 equals 0 and f of 1 equals 1. So I can't say we have a cool twist on something if I don't show you what we're twisting, right? So we want to find the formula of the sum of the first n Fibonacci numbers. I propose that it gives us the n plus second Fibonacci number, all minus 1. We'll prove this by induction. We'll do 3 base cases just to be sure that it works. N equals 0, n equals 1, and n equals 2. For n equals 0, we get a pretty trivial case where you just get the single Fibonacci number at 0, which is 0. So we know that the second Fibonacci number is 1 because it goes 0, 1, 1. So we have 1 minus 1 equals 0, which gives us our base case, our first base case, I should say. For n equals 1, we get 0 plus 1, which is 1, which is the same as 2 minus 1, and 2 is the third Fibonacci number. What about n equals 2? So for n equals 2, we get 0 plus 1 plus 1, which is 2, which is the same as 3 minus 1. And we know that 3 is the fourth Fibonacci number, so it works. Now let's say that this is true for n equals m, where m is some number greater than or equal to 0. Some integer, I should say. And we want to show that it is true for n equals m plus 1. So we can take the sum from k equals 0 to k equals m plus 1 of f of k. Well, if we take that, we can actually take out the m plus 1th term and put it on the outside to get f of m plus 1 plus the sum from k equals 0 to k equals m of f of k. And since we know by induction that for n equals m, then the sum equals f of n plus 2 minus 1, then we get f of m plus 1 all plus f of m plus 2 all minus 1, which by the definition of the Fibonacci sequence, 2 successive Fibonacci numbers added together gives the next one. So f of m plus 3 minus 1, which is m plus 1 plus 2. Hence, we are done. A little background. So the original question we were trying to show had 1 over 2 to the k in it, right? Let's take a look at a little calculus. So we know that from calculus 2 or calculus C, depending on which you took, that the geometric series from 0 to infinity of some base value, a, times r to the k, where r is the base of the exponent, equals a over 1 minus r, when r obeys the following inequality, -1 to 1, non-inclusive. We can find the sum in the following way. Say that the partial sum, s sub n, the nth partial sum, equals from k equals 0 to k equals n of a times r to the k. That gives us the following, just based on taking each term and adding it together. If we take r times that, we actually get a times, well, it's everything shifted up by an r, right? So it's, instead of 1, it's r. Instead of r, it's r squared. All the way up until, instead of r to the n, it's r to the n plus 1, right? So then we can take r times s sub n plus a. Well, okay, so that just gives us a one more in the parentheses of what you have to distribute. So it's a times all that. But the first n term, actually n plus 1 terms, because you have a 0, the first n plus 1 terms of that would give you just s sub n, right? So you can actually take that out and get s sub n plus a times r to the n plus 1. We can then get s sub n in terms of other things. So we have 1 minus r times S of n equals what we have there, which equals a minus a times r to the n plus 1, which then we have equals a all times 1 minus r to the n plus 1. Well, finally, we can divide 1 minus r from both sides to get S of n equals a all times 1 minus r to the n plus 1 all over 1 minus r, which is true for all r not equal to 1. For the case r equals 1, we simply get, well, 1 to the any power is just 1, right? So we get just summing a n plus 1 times. So that gives us n plus 1 times k. And that, I meant to put a there, sorry. That is n plus 1 times a. So if we take the limit of S of n when r does not equal to 1 as follows, we get the limit, well, the limit as n approaches infinity, I should say. We get infinity for r greater than 1 because you get 1 minus some number greater than 1 is a negative number, and then 1 minus some number way bigger than 1, you get 1 minus infinity, right? 1 minus infinity times all times a, which is still just negative infinity, over a negative number, which gives you infinity. And it goes alternating between plus and minus infinity for r less than negative 1 when because depends on the power, if it's an odd or even power. So when r equals 1, we get this the limit n plus 1 times a equals infinity. Because as n goes to infinity, then infinity times a positive constant is also infinity. When r equals negative 1, then the function alternates between S of n equals 0 and S of n equals a, when n is odd and even respectively. However, when r is within the bounds we discussed earlier, then the limit of r to the n plus 1 equals 0 because n goes to infinity and something between negative 1 and 1 gets smaller and smaller every time you multiply it by itself, right? Or, well, the absolute value gets smaller and smaller, which means it goes to 0. Meaning that the limit really just goes to a over 1 minus r, which gives us exactly what we mentioned before. I hope that is a good background. So more background. So to remind us, the question we had in mind is the k plus 1th Fibonacci number over 2 to the k, and you're summing that from 0 to infinity. Does the background we used give us the solution to the problem? Well, not quite. Because even though we could rewrite the denominator, we still have f of k, which is not constant for the terms of the sum. If it was constant, we could just use f of k equals a. So, what could we do to solve the problem? Well, there are two ways to really go about it. One way is to analytically solve each term by finding an exact formula for f of k and simplifying the sum in any way we can. That is the second method I will show you because it is much more math intensive, but the first method I will show you is a probabilistic proof. By that, I do not mean in the sense of existence proofs, where if something may exist, then it must exist, but instead in the sense of using probabilistic models to exactly find the value. One of the axioms of probability theory is that the probability of a sample space is equal to 1. We will use that to our advantage. First, an easier example. So, given the set of all possible combinations of coin flips of a fair coin with heads or tails, we know that it creates a sample space because it has clear defined rules on what the possible outcomes are. What is the probability of heads on a fair coin? Well, 0.5. What about tails? That's also 0.5. Okay? So, however, that is just a sample space of a single coin flip. If you do 2 distinct coin flips, you will receive a probability of 0.25 for each equally likely outcome. As you continue this, you get each successful flip gives you 2 new options that gets tacked on to the end of each other possibility, making the probability from 1 to 2 to the n different possibilities of 1 over 2 to the n probability. So there is 2 to the n different possibilities, each with a probability of 1 over 2 to the n, which gives you a total of 2 to the n over 2 to the n, which equals 1. A second example that we could use, right? So a second example, if I take the set of all possible combinations of coin flips until I receive heads, with a condition that I stop flipping once I receive heads, then the only option is if I receive tails n minus 1 times and heads once, giving me the sum of possible probabilities. K equals 1 to n of 1 over 2 to the k, right? Because it's only possible to have heads, then tails heads, then tails tails heads, so forth in the sample space. And each one of those has a probability of 1 over 2 to the k of happening. This is the sum of n possible combinations with probability p of k equals 1 over 2 to the k. Because each time I flip another coin, there's a probability of a half of getting heads. Since each flip is independent, then you can multiply the probabilities. However, there is an infinite number of combinations because you could never reach heads. I mean, if you reach heads, then that's fine, but you could just keep getting tails forever, right? So the actual value is k equals 1 to infinity of 1 over 2 to the k. Well, okay, so if that's the case, then we can just use the geometric series formula that we showed earlier, which is 1/2 over 1 minus 1/2, which is just 1/2 over 1/2, which equals 1. And by the geometric series formula we derived earlier, this verifies that this indeed is a sample space if we had any doubts. We can kind of generalize this. So we can go to the next problem, which is defining the sample space such that all combinations of fair coin flips until you receive heads twice in a row, rather than once. Well, how many combinations of a given length are there? And what is the probability of each combination? Well, firstly, the probability of the combination is the same as before, since it is a fair coin. For some combination that ends at k total flips, the probability of receiving that combination is 1 over 2 to the k, since it is a fair coin which is independent. Let's define lowercase f of k to be the number of possible combinations with exactly k flips. And let's define f sub h of k and f sub t of k to be the number of possible combinations that start with heads and tails respectively. Therefore, pretty clearly, the total number of f of k is equal to f sub h of k plus f of t sub k, because it can only start with heads or tails. I propose that f of k equals the k minus 1th Fibonacci number. To prove that, we can use induction. The first base case is k equals 1, because there is no negative first Fibonacci number. And for k equals 1, we get f of k equals 0, which equals the 0th Fibonacci number, which is the 1 minus 1th Fibonacci number. Because if you only flip the coin once, it is impossible to get heads twice. So the base case holds. If you're a little skeptical, we can do the base cases for k equals 2 and k equals 3 as well. Well, the only option for k equals 2 is heads heads. So f of 2 equals 1, which equals f of 1, which is, well, capital F of 1, which is capital F of 2 minus 1. For k equals 3, you cannot have heads first, because the only options are heads heads heads, heads heads tails, heads tails heads, and heads tails tails, and none of those end when they flip to exactly 2 heads. Therefore, the only possibility is tails heads heads. Therefore, f of 3 equals 1, which equals capital F of 2, which is the same as capital F of 3 minus 1. We just showed 3 base cases, so assume it is true for k equals n minus 1 and k equals n. Then we need to prove that it is true for k equals n plus 1. And the reason we can do k equals n minus 1 and k equals n is because we proved it for 3 base cases. We only needed 2, but it works for 3. So, since f of k equals f of h of k plus f of t of k, we can use that to our advantage. However, if a combination of length k starts with heads, then a combination of length k plus 1 that starts with either heads or tails, followed by the said combination of length k, would have to start with tails. Otherwise, you would start with 2 heads in a row and the sequence would be finished right away. Similarly, if a combination of length k starts with tails, then a combination of length k plus 1 could start with either heads or tails. if it follows afterwards. Meaning f sub h of k plus 1 equals f sub t of k, because those are the only combinations that start with heads. Furthermore, since the combination of size k plus 1 that starts with tails could have a combination that follows it of size k with either heads or tails starting it, then f sub t of k plus 1 equals f sub h of k plus f sub t of k, which equals just f of k. Finally, we can put that together to get f of n plus 1 equals f sub h of n plus 1 plus f sub t of n plus 1, which is also equal to f sub t of n plus f of n, because we made the substitutions for f sub h and f sub t, which then we can make this another substitution for f sub t to get f of n minus 1 plus f of n, which we know that from the assumption that for f of n minus 1 and f of n, we get capital F of n minus 2 and capital F of n minus 1, which overall we get capital F of n. Therefore, since f of n plus 1 equals capital F of n, we get f of k equals capital F of k minus 1. Well, what are the next steps, right? So, since we know that the number of possible combinations of a given length k is the k minus 1th Fibonacci number, and that each combination of length k has probability of 1 over 2 to the k of appearing, and this is in fact a sample space, then we finally get the sum from k equals 1 to infinity of capital F of k minus 1 over 2 to the k, which we know it's a sample space, so it equals 1. We know that f of 0 equals 0, so we can actually do the following. We know that f of k minus 1 at k equals 1 is f of 0, which equals 0. So we can start at 2 instead of 1. So we get the sum from k equals 2 to infinity of f of k minus 1 over 2 to the k, which is the same thing by substitution of variables of k equals 0 to infinity of f of k plus 1 over 2 to the k plus 2, which we can pull out a 2 to the 2 from the denominator to get 1/4 times the sum we were originally looking for equals 1. Therefore, we can multiply 4 to both sides to get the solution to our original equation, which is 4. When we use Binet's formula, which is a non-iterative solution to the kth Fibonacci number, which is f of k equals 1 plus the square root of 5 all to the k, minus 1 minus the square root of 5 all to the k, all over 2 to the k over square root of 5. This is called Binet's formula, and we will use induction to prove this. So, the base cases are k equals 0 and k equals 1. Therefore, respectively, we get, well, plugging in 0 for k, everything cancels out in the numerator. So we get 0, which is true. And for 1, well, the 1's cancel out, and then it just becomes 2 square root of 5 over 2 square root of 5, which equals 1, which is the first Fibonacci number, indexing at 0. So therefore, the two base cases work. So now assume it is true for k equals n minus 1 and k equals n. Then we need to show that it is true for k equals n plus 1. We'll use the following. So f of n plus 1 equals f of n plus f of n minus 1, which equals 1 plus the square root of 5 all to the n minus 1 minus the square root of 5 all to the n, all over 2 to the n over square root of 5. That is just the f of n term. The f of n minus 1 term is 1 plus square root of 5 to the n minus 1 minus 1 minus square root of 5 to the n minus 1 over 2 to the n minus 1 over square root of 5. When we multiply the second fraction in the equation by 1 minus square root of 5 times 1 plus square root of 5 all over itself, we get that's the same as negative 4 over negative 4, which equals 1. So that's why we can multiply it. when we multiply the respective binomials, we get, instead of n minus 1 in the power, we get n in the power. Then we get multiplied by conjugate of it. So overall, this gives us something that we can reverse distribute, right? So we can multiply the first fraction by 2 over 2, which equals 1, which is why we can do it, to get the 2 to the n plus 1 in the denominator, which finally combines to, as you see there, which is exactly what we said the formula would be for n plus 1. So we just proved it. So the second solution to the problem is using that formula. Remember, the problem is to find the value of k equals 0 to infinity of f of k plus 1 over 2 to the k. This is the same as finding the following sum. That is because I separated each individual part into its component to the k power times another component that is not to the k power by its constant component. Which, taking the geometric series formula, which is very convoluted, which is why I kind of did this second, you get 1 plus square root of 5, so forth, which is very convoluted. So that's why I kind of waited to do it. You get that whole thing, which all simplifies after a very long time to 4. It simplifies to 160 over 40, which equals 4. In conclusion, I feel like it was a very interesting question. The second proof seems very convoluted, like I said before. If you make a single mistake somewhere, small, it has major consequences on the answer, which, trust me, I made a bunch of mistakes while typing this solution. That being said, if you are able to find a very simple parallel way to ask a question that has a more elegant solution, try to think out of the box and come up with a new way to look at an old question. I am unsure if this question has ever been asked, but I got the inspiration while doing another question, which this was a byproduct of. New ideas are always needed in fields of research of mathematics. I hope someone can find inspiration from this. Feel free to subscribe. I'm currently working on my math graduate degree, and I feel like this is a good way to kind of share my love of math for everyone else. Thank you. Bye-bye.